be timely.
Yeah.
So thanks everyone for joining us, the in-person participants and the virtual participants. I'm excited for this series of talks that we have this next 2 days. We're gonna begin with Carl. I always have problems with your last name, Liechty.
But yeah.
And he's gonna give us an introduction to the six-vertex model. Carl's a professor at DePaul University, and he's literally wrote the book on the six-vertex model, or a book. So I'm very excited to hear him give us an introduction to the six-vertex model.
All right, thank you, Axel. Thanks so much for putting on a conference and for inviting me. I'm really happy to get out of the city sometimes and see trees and mountains. So I appreciate that, and do some math as well. My goal is to say as much as I know about the six-vertex model in an hour. So I'm gonna start at the beginning, which as far as I can tell is in 1935. And I'll talk about some developments in this thing called the six-vertex model up through like last month or something. But this is a very incomplete history. So if you know something about the six-vertex model, you've done some work, I probably will miss your your contribution. So, but this is what I know. So yeah, so this six-vertex model is a pretty famous model in two-dimensional statistical physics. And originally, the kind of origin of the model, I think, is in this paper, which says something about the structure and entropy of ice. So this is supposed to be a model for ice crystals. And the author of this paper was Linus Pauling. And this is a picture of Linus Pauling 100 years ago in 1922, upon his graduation from Oregon. It wasn't called Oregon State University then, it was called something else, but from this university. So that's a nice connection. So he was trying to understand why ice crystals have some entropy at very low temperatures, and that involves understanding the different ways that ice crystals can form. And so I just copied something from his paper here. I guess this is a good model for ice crystals. Each water molecule is supposed to be oriented so that it's two hydrogen atoms. Water is H2O. Its two hydrogen atoms are directed approximately toward two of the four oxygen atoms which surround it tetrahedrally. Okay, so what does that mean? What's that? Doesn't look like what?
There are four white dots.
That's true. So there's an oxygen atom here, and you can imagine I only drew one of the oxygen atoms, but you can imagine a lattice of structures like this, where there's an oxygen atom in the middle, and around it are four hydrogen atoms. And then there will be another oxygen atom over here, which is kind of close to this hydrogen atom. And the bond is formed, it's H2O, so you have to choose of the four hydrogens around the oxygen, you have to choose two of them to make bonds with. So maybe it'll bond with this one and this one, and then this hydrogen is gonna have to bond with a different oxygen that's surrounding it on the lattice, okay? Okay, so this is, I guess, the origin of the entropy of ice is that the oxygen has to choose of the four hydrogens around it, it has to choose two oxygens to bond with. And I did not draw the whole three-dimensional tetrahedral lattice because I can't do it. I'm not very good with three-dimensional pictures. But the lucky thing is we can get the same statistics by drawing just a square lattice on the plane. And And right, so I can draw a lattice of hydrogens with, or sorry, lattice of oxygens with hydrogens around it. 4 hydrogens surrounding each oxygen on a square lattice, and still I need to choose 2 of the 4 hydrogens around each oxygen. So this is a 2-dimensional model, which is supposed to be a very good approximation for a 3-dimensional model of ice. And I guess it works pretty well. Yes, got it.
What do you mean by we get the same statistics?
I meant that in a very rough way. I mean, there are, each oxygen has 4 hydrogens surrounding it, and you choose 2 of them.
So locally, locally it looks similar. But
very locally, it looks similar, yeah. But globally, yeah, then it's, yeah. Yeah. Okay, so this is the picture that is easier for me to understand and that has been studied quite a bit since 1935. Often, instead of drawing hydrogens and oxygens, we can just draw a square lattice here and draw arrows on the edges of the lattice. So I'm imagining that there's an oxygen at each vertex of this lattice, and there's a hydrogen on each edge. And if there's a bond between the hydrogen and the oxygen, then I draw an arrow toward that oxygen. Okay, so like this vertex here, the arrows on the edges that point in towards the vertex are on the top and the right, and that corresponds to hydrogens on the top and the right being bonded. Right. Okay, so that's a model, and there's many ways to draw arrows on this lattice. And the rule is I'm supposed to have exactly 2 bonds, which means I have to choose exactly 2 arrows that point in toward the vertex and 2 arrows that point out. And there's how many ways to do that? 4 choose 2, which is 6. So that's why this is called the 6-vertex model. And these are the 6 vertex types. 1 and 2. 1 and 2 are similar. I don't know if you can see. Vertex type 1 has 2 up arrows and 2 right arrows. And vertex 2 has 2 down arrows and 2 left arrows. So those are related by just a flip. And similarly, 3 and 4 are related by a flip. And 5 and 6 are related by a flip. So somehow the 1 and 2 are similar and 3 and 4 are similar. Sometimes you'll see a picture of the 6-vertex model without any arrows, but instead as some kind of non-intersecting paths on the square lattice. So there's a kind of bijection between the 6 vertex types and some darkening of the edges of the lattice. And this is what the rule is. And so this configuration here, if I darken the edges according to this rule, is looks like these 4 non-intersecting paths in the lattice. I'm not going to use that picture very much, but maybe you've seen it before. Okay, so there's many different ways to draw these arrows on the edges, and we can make a probability measure on the collection of all the possible configurations of arrows. And the typical way to do it in statistical mechanics is to assign a local weight to each vertex type. So to each of these 6 vertex types, assign a number, positive number, and then the weight of any particular configuration is just the product of the weights of all the vertex types in the configuration. So I have these 6 weights, and I just count how many vertices there are of type 1, multiply W1 by itself that many times. Same with vertex type 2, 3, 4, 5, and 6. Okay. Okay, and then the probability measure is just given by the weight of each configuration divided by the normalizing constant, which makes it a probability measure. And that's called the partition function. It's just the sum of the weights of all the possible configurations. Okay, so that's that's how we can make a probability measure, and you can choose the weights. If you choose a big weight for vertex type 6, then you're going to tend to see configurations that have a lot of vertices of type 6. Originally, Pauling was considering that all the weights are the same. All the weights are just 1, and then you're just counting how many configurations there are. So the main physical question, at least for Pauling and for work that came directly after that, was to understand entropy, which has something to do with how many different configurations there are. And so typically, this partition function, which in the case of equal weights just counts how many configurations there are, for large n, and maybe I didn't mention it, I'm always considering this square lattice to be of size n by n. So it's a square, n is the dimension, so n squared is the number of vertices. I did not specify the boundary condition. All of my pictures are all the same boundary condition, so, but it's okay. I will specify the boundary condition. Yeah, so typically for large n, the partition function grows like e to the power n squared times some constant, which somehow, which I'm calling f here. And for Pauling and these guys whose pictures are below, the main question was what is this this constant that governs the rate of growth? So that's in statistical physics, it's called the free energy. And so they really wanted to know what the free energy was. Pauling, in his first paper, he wrote down some number for the free energy, which I don't think was correct actually. But 30 years later, these guys, this is Elliot Lieb from Princeton and Bill Sutherland from Utah. I think he did this work as a graduate student, but he had a long career at Utah. They were able to calculate the free energy. Lieb had, I think, 4 papers that dealt with various weights, and Sutherland had a paper that I think dealt with a pretty, I don't remember exactly, he dealt with a pretty general class of weights. So they used the method of transfer matrix, which was well known because it was also used to solve other models in statistical physics, like Ising model. Okay, so I don't want to talk about that, but that's a major development in this story. 30 years after Pauling. And then another, how many years later? 25 years later. Oh yeah, so I guess there was a question about boundary conditions. They were considering always periodic boundary conditions. So this is really the model on the torus. Because that's the easiest way to apply the transfer matrix method.
Sorry, it's the easiest method to apply.
The periodic boundary conditions are kind of natural for the method of transfer matrix. Okay. It's the most straightforward way to go. But some different boundary conditions were introduced by Vladimir Karepin in 1982. And these are the boundary conditions in which all the arrows on the top and the bottom point in, all the arrows on the left and the right point out. So these are some fixed boundary conditions. And if you're looking at the non-intersecting paths picture, it means the paths all enter from the top and they all exit from the left, or maybe they enter from the left and exit from the top. I'm not sure. So these are the boundary conditions that I want to focus on for the rest of the talk, because this was 40 years ago, and there's been lots of very interesting questions that some of which have been answered and many of which have not been answered. So, so this is the focus for the rest of the talk. Okay, so why? What's so great about these particular boundary conditions? One thing is there are other ensembles in combinatorics and probability, which are generalized by this six-vertex model with domain wall boundary conditions. So for example, let me make this a little bigger. If we use this rule here, where we replace all the type 1 vertices with a little shape like that, and all the type 2 vertices with this shape. Similarly for 3, 4, and 6. And yeah, so if we follow this little rule, then what we'll end up with is a picture of domino tilings. And these are domino tilings with a very specific shape. So this is called domino tilings with of the Aztec diamond. So they have this zigzag boundary condition. It's not exactly a one-to-one map because there's a very specific rule for what to do with all the vertices of type 1, 2, 3, 4, and 6. But the type 5 vertices, we have to make a choice. We either do a diagonal up or a diagonal down. And they both fit, and they'll give different tilings of the Aztec diamond by dominoes. But nonetheless, up to that little choice, a six-vertex configuration corresponds to some family of Aztec diamond tilings. And you can get all the information that you want about domino tilings from questions about the six-vertex model. Of course, the six-vertex model is kind of a bigger model because when we make these domino tilings, we don't see all 6 vertex types really. We see just which type of dominoes we have, the upright ones and the downright ones. So yeah, so somehow the Aztec diamond domino tilings are a more restricted model than the 6-vertex model. Okay, so this is something that that we can study using the 6-vertex model. There's another well-known model or well-known question in combinatorics about alternating sign matrices. So this is an alternating sign matrix on the right here. It's a matrix with 1s, 0s, and -1s. And the rule is that along every row and every column, well, okay, there's several rules. Along every row and every column, the sum should be 1, and 1s and -1s should alternate. Okay, so along the first row, the sum is 1. Second row, so sum is 1. The third row, okay, the sum is 1, and I stick a -1 in there. So it's because the sum has to be 1, I always have to go 1, -1, 1, -1, maybe with some zeros stuck in between. All right. So
question.
Yes.
Why were people in combinatorics looking at alternating sign matrices? Are they counting something in particular?
Yeah. So there's I guess a theorem now. It was a conjecture for many years that that the enumeration of alternating sign matrices is related to the, oh man, I'm gonna probably mess it up. Somebody probably knows it better than me. Totally symmetric plane partitions, I think. Greta, is that right? Totally symmetric.
They happen to be the same number.
Yeah.
And there was this Niels-Robbins conjecture.
Yeah.
I don't know originally why they were looking at alternating sign matrices.
So I think originally, there was this thing called the lambda determinant, which is a totally different story. So there's a formula for computing determinant, which is called Dodson condensation. And it represents a determinant of a matrix in terms of the determinants of the minors. And it's like, yeah, there's a formula, there's a difference between two minors in the formula. And if, so I can even write a picture here. Okay, it's like the determinant of this minor minus the determinant of this minor divided by something, I forget. Yeah, okay, sorry, I'm gonna write the wrong thing. So that was, yeah, that's called Dodson, the Dodson formula for determinant. And somehow, if you use the same formula, but instead of just subtracting, you add a constant times the determinant of the minor, you get this thing called the lambda determinant. And it turns out there's an expansion for the lambda determinant, just like the expansion in terms of, what is this called? Expanded determinant, you take something from the top row times something from the second row. Laplace expansion, thank you. Yeah. So there's a formula for this lambda determinant, and instead of having n factorial terms, instead of oh man, I'm messing up the whole thing. Instead of having okay, there's a formula in the expansion, and the coefficients in the expansion are the enumeration of the alternating sign matrices. That's I think the origin of the alternating sign matrices.
More than n factorial?
No, it's less than n. Yeah. Whoops. Okay, so I apologize if I said something wrong there, but yeah. But yeah, so that I think is the origin, but then it turned out these guys, Mills, Robbins, and Rumsey, were looking at this and they noticed that this seemed to be the same enumeration as this totally symmetric plane partitions. And so there was a lot of interest. This was the number that they said counted the number of alternating sign matrices. And so this was a conjecture that this is the number of alternating sign matrices, which was proved by Zeilberger in 1995 and almost immediately after by Kuperberg. So what's the relation to six-vertex model though? Well, here's the relation. So these type 5 and type 6 vertices are different than the others in that these are the ones where the arrows can switch from left to right or from right to left if you're looking along rows. The other vertex types arrows are aligned. And so the domain wall boundary conditions kind of force us along each row to have a switch somewhere because the arrow starts to the left, it has to end to the right. So somewhere along that first row it has to switch. And the boundary conditions on the top force us to have exactly one place where there's a switch. So in the first row, there should be exactly one vertex of type 5. And it's colored in here in red. Okay. And then in the second row, well, I have to have a switch somewhere. I might have a switch. So I have to have a vertex of type 5 somewhere. I could have more than one. I could have 5 and then a 6 and then a 5. I could switch once, switch again, and switch back. But always along each row, vertices of type 5 and 6 have to alternate, and they have to start with 5 and end with 5. And so if I take my 6-vertex configuration and replace all the type 5 vertices with 1s and all the type 6 vertices with -1s, I get an alternating sign matrix. Right? And again, there's less information here because everything else I put a 0 in. And so the alternating sign matrix ensemble doesn't tell me anything about how many type 1 vertices there are versus type 2, because they all get squashed together as zeros.
So it's kind of like you're specializing those weights to be 1.
I'm specializing those weights to be the same, I guess. Yeah, exactly. Yep. Okay. So there's another big kind of interest for these domain wall boundary conditions. Let me try to describe what the phase diagram looks like here. So there's 6 weights, which are the parameters in this model. It turns out that with the fixed boundary conditions, you always have the number of type 1 vertices and the number of type 2 vertices is the same. It doesn't, it's just in the combinatorics. And so, so it doesn't, you don't lose anything by just giving those the same weight, which we can call A, and the same with type 3 and 4, I can call those B. And 5 and 6, we just saw there's not exactly the same number of 5 and 6 vertices, but they differ by a constant, by n. So, okay, so I can give those the same weight. So really, there were 6 parameters. Actually, there's only 3, A, B, and C, and we can not lose any generality by forcing one of them to be 1. So, so there's really 2 parameters, like A divided by C and B divided by C. And so this is a picture of the axes A over C and B over C. And it turns out if either A or B is much bigger than C, then the model really likes to see vertices of that type. And we call this the ferroelectric phase. So ferroelectric means that the arrows tend to be aligned. They tend to not switch directions. Okay. And so there's 2 different ferroelectric phases, when A is really big and when B is really big. And so these are the 2 regions of the phase diagram, which correspond to a big A and a big B. You could have that C is much bigger than either A or B. C is much bigger than A or B, which the transition happens when C is bigger than A plus B. Then the model wants to see as many switches as possible. In the alternating sign matrix picture, it wants to see as many 1s and -1s as possible. And that's called the anti-ferroelectric phase, which is down here in the picture. So that's when the denominator is big. And if A, B, and C are roughly about the same size, which means I can make a triangle with them, then nothing is really favored very, very strongly, and we have a disordered phase. So that's this region here in the phase diagram. The diagonal, that's when A is equal to B, as Axel pointed out. That's the line that that corresponds to the alternating sign matrices. And there's also a little circle in here where A squared plus B squared equals C squared. And that's the points in the phase diagram that correspond to the Aztec diamond tilings. Sometimes that's called the free fermion line, because everything corresponds to a dimer model there.
Is it determinantal?
It is determinantal, yes.
Along that.
Just along that axis, yep. That's right.
And is that a particular value of delta?
That is delta equals 0, yeah. Yeah, so delta is a squared plus b squared minus c squared. That's some parameter. If a squared plus b squared equals c squared, it's 0. All right. So that's what the phase diagram looks like. It turns out for these boundary conditions, domain wall boundary conditions, there's actually an exact formula for the partition function, which is really nice. It's written here. This is called the Issergen-Karepin formula. It's some explicit factor times this thing I'm calling tau, and tau is it's a Hankel determinant. So it's a determinant of a big matrix of size n by n. And the entries of the determinant are derivatives of some function. And the function I take the derivatives of are given in terms of the weights, but I have to parameterize the weights in the right way. So it's convenient to use a parameterization, slightly different parameterization in each of the phase regions. So in the disordered phase, I use parameters t and gamma and parameterize the weights a, b, and c in terms of sine functions. So similar in the anti-ferroelectric phase in terms of sinh functions, and sinh also for ferroelectric, but different values of t and gamma. So yes.
So here for the domain wall boundary condition, you choose the symmetric parameter for different weight, right? There should be 6 different parameters. You choose the symmetric weight.
There should be 6 different parameters, but in fact, for fixed boundary conditions, you don't lose any generality. The Gibbs measure is exactly the same as assuming that weight 1 and weight 2 are the same.
Right.
And weight, yeah.
So is there any different way for us to choose these parameters besides the symmetric way that you use a1 equals a2 equals a?
No, it doesn't change the model at all if you choose different weights. Okay, so that's the formula. This phi function that I'm taking derivatives of is just very simple. It's c divided by a times b with this parameterization, and the derivatives are all with respect to the t variable. I should mention the history here. So this formula was proved by Issergen in 1987 based on some kind of recursion that was in the original paper of Karepin in 1982. So that's why it's called the Issergen-Karepin formula. If you're interested in what these words mean, the whole thing is based on the Yang-Baxter integrability of the model, which I won't discuss at all, but I'll just say the words. So there's a connection of this Issergen-Karepin formula to random matrices, which was noticed by Paul Zingerstan in the late 90s. So this is what he noticed. If somehow I'm able to write this phi function, which is the symbol in the Hankel determinant, as the Laplace measure, or Laplace transform of some measure on the real line. So I don't know what this d mu is, but if there's some d mu, so that I can write it like that, then derivatives just become multiplication by x. And I can do a little bit of linear algebra and pull all the integrals out of the determinant and end up with a big multi-integral of a pretty simple determinant. This is the Vandermonde determinant. Just has different variables x to successive powers. And there's a nice simple formula for the determinant of the Vandermonde matrix. It's just the product of the differences of the variables x. So that's by now a pretty standard computation, which was known pretty well to people working in random matrices. And Zingersan noticed that this is exactly the same, at least in formally, as the partition function for unitary invariant complex Hermitian random matrices, which happened to be a subject of a lot of study around the time in the mid to late 90s. And so he kind of exploited this fact and this connection to compute the free energy of the domain wall boundary condition six-vertex model in each of the phase regions.
For this to be true, do you need to know what mu is?
Yeah, so you have to compute, you have to figure out what mu is, and he did that. It's different in each of the phase regions, and so it's a different computation in the three different phase regions. Yeah, so he did that. It's not completely rigorous what he did, and so.
Sorry, which part of it is rigorous?
Well, I mean, that's a good question.
That's good.
I mean, I think the analysis uses some ansatz on what the form of the asymptotic should be, and then apply some differential equation to that, and then you apply the differential equation to the ansatz, and you get the answer. But there's some gap there. Yeah. But this presented a nice opportunity for people that like orthogonal polynomials to do some really nice work. So the method in random matrices to compute the asymptotics of the partition function was to rewrite that big multiple integral in terms of orthogonal polynomials. And you can do the same thing here. So this, if you introduce some monic polynomials of degree j, so this is a system of polynomials which are orthogonal with respect to the measure e to the tx d mu, whatever the mu is. So that means this integral is 0 if the degree is different, and it's some positive constant if the degree is the same, which I call hk. Then in this van der Waals determinant, you can just use row operations to replace all of the monomials with monic polynomials. You can choose them to be those orthogonal polynomials. And determinant of the square of the Hankel determinant then becomes a big multiple integral. I'm just expanding the determinant here of that van der Waals. And there's many, many terms here, some. But because the polynomials are orthogonal, when we integrate, most of these terms are going to be 0. The only ones that aren't 0 are the ones where the polynomials are squared in each variable. And so what we get is each time I get kind of the diagonal term when I multiply out this, this big square of n factorial terms, each time I hit the diagonal term, I get the product of these normalizing constants, hk, and then I'll get n factorial of them because there's n factorial terms in our big sum. And so it just cancels an n factorial in the formula for tau. And so the relevant point of analysis is to find the product of all the normalizing constants in your system of orthogonal polynomials up to n-1. Yes. What's that?
In the first integral, what is
In the first integral, Oh, that's a T, sorry. That's a T. So T is the parameter. Yeah.
I'm referring to the first integer.
The first integer, oh, up here. That's also a T. Yeah. Okay, so the problem becomes a problem about the asymptotics of these orthogonal polynomials.
Did each case depend on T then?
HKs do depend on T, yeah, that's right. So for certain values of T and gamma, these are actually classical orthogonal polynomials, and you can open a book and look through the book and try to find exact formulas for the H's. And that's what two physicists, Colombo and Prunko, did in a paper from 2006. But in general, these are non-classical, and it's a pretty hard problem to understand what the orthogonal polynomials look like. But this guy could do it. This is Pavel Bleher, who kind of initiated a program to study the asymptotics of this partition function by orthogonal polynomials, starting in 2006 in a paper with Vlad Fokin. And then I was involved in several papers after that, and Thomas Butner was also involved. But this was a 6-year program because you have to do things separately in each of these phase regions. And we wrote a book about it too. So if you're interested in seeing it all in one place, you can look there. Okay. Okay, so I'm not going to write any of the results there, but there's another nice story there. I want to talk for the rest of the time about not about the asymptotics of the partition function, but about the kind of statistics of the states themselves. So so these conditions. So as we saw when we were looking at the mapping to alternating sign matrices, they really enforce a really strict ordering at the boundary. So like along the first edge, or along the first row, you'll see exactly one type 5 vertex, and everything is fixed to the left of that, and everything is fixed to the right of that. So there's a strict ordering enforced by the boundary, but if you're in the disordered phase, for example, then the model wants to see disorder. And so there's kind of a competition between the boundary effect and the local interactions. And the result is that you see pictures like this. I don't know how well we can see that, in which in the corners, things are completely frozen. Typical states are completely frozen, I should say. So it's overwhelmingly likely that all the vertices in the top left corner are of type, I forget which type is in the top left, the one that looks like that. And it's overwhelmingly likely that all the vertices in the bottom right are going to look like that. Okay. But in the middle, we see a region of disorder. This is the disordered region. And there's a really sharp boundary between the region of disorder and these frozen regions. And that's called the Arctic curve. It separates the frozen piece from the non-frozen piece. Yeah.
Can you describe how this is generated, this picture?
Not very well. So I took these from a paper by Reshetkin, Nikolai Reshetkin, and his collaborators, Allison. So, what are you looking at? So I think they, yeah, so you can think like each vertex type is shaded a different color.
Okay.
I think they might have been using the lattice path picture instead. And so, yeah, I guess here is where there's no lattice paths at all. So that's looks empty are dense, and here's the lattice paths are doing just a turn everywhere, and here is where they're all mixed up and disordered. Does that work? Yeah. Yeah, so these are three pictures that they generated in the disordered region. The anti-ferroelectric region is even more interesting. So that's where you want to see the type 5 and 6 vertices. We're going to see lots of switches. But you still get these frozen regions. So this is just this picture I can describe. This is a density of the type 5 and 6 vertices. So there's none of them in the corners, and there's a lot of them in the middle, but it's not totally frozen. So the middle's not completely white. There's like these little islands of non-type 5 and 6, and in between there's a disordered region. So this is a very interesting picture.
I have a question.
Yep.
How about the statistics? Do we know anything about the fluctuations? Or
it's a great question, Axel.
Yeah. The island in the middle, are they parking effects or are they really?
They're really there, I think. There's no math results, and I don't even know of any physics results, but they seem to be really there. Yeah, so the big questions here, try to describe the shape of this Arctic curve when n gets big. And once you try to describe the shape, you can try to ask what the fluctuations look like around that Arctic curve. And so what can we say? In the special case of the Aztec domino tilings, we can answer those questions really nicely. In that case, the Arctic curve is actually a circle, which was proved in the 90s by these people, Jokish, Prop, and Shore. And then the question of fluctuations in that case was tackled by Kurt Johansson, who showed that the fluctuations are given by the Airy process, which is a stochastic process whose marginals are the Tracy-Whittem distribution, which describes the largest eigenvalue in a random complex Hermitian random matrix. So there's a real random matrix connection. The last random matrix connection was just at the formal level, but this is a real connection to a probability distribution from random matrices. In the case A equals B equals C, so that's the alternating sign matrix case, and also in the free Fermion case, there's another result, which is that if you look near the place where the Arctic circle just touches an edge, so you look just close to the boundary, and you look at the statistics of the ones in the alternating sign matrix, they are the same locally in some scaling limit, same statistics as a different random matrix ensemble, which is called the GUE corners process. So this is a process in which you fill in a matrix with a Hermitian matrix with complex Hermitian entries. And you look at the eigenvalue of the top 1 by 1 corner, and that'll be the same as the distribution of the top 1 there. And you look at the eigenvalue of the top 2 by 2 corner, and that'll give you the distribution of the ones in the second row, after some rescaling, of course, in a limit. Top 3 by 3 tells you where the ones are in the third row. So that was a connection originally for the free Fermion case. by Johansson and Nordenstam, and for the alternating sign matrix case by Vadim Gorin more recently.
So do we also know something about minus one?
I don't know. It's a good question. I don't know. Seems like we should, but.
Sorry, what was the question? I'm asking, do we also know the information for where that is minus one? Okay.
Yeah, so this is just about the ones, but where are the minus ones? They're somewhere in between. But
Yeah, you can get it right.
so it's kind of dual or something.
Between this triangle that you drew there and what's called monotone triangles. Just record the positions of the ones in their place.
Okay.
And then you can in some sense really derive that, but then the statistic doesn't really keep track of that very well. The one that uses the view.
Okay. Yeah, so this is, the positions of the ones is discrete. The left is discrete, the right is continuous, but this is after some scaling limit. So in the scaling limit, it becomes continuous. Okay, so those are the results on the Arctic curve that are kind of rigorous in the math literature. In physics literature, there's more results. So there's a couple of different approaches. One approach is to study what's called the emptiness formation probability, which is a probability depending on two parameters, R and S. It just asks, what's the probability that the top R by S corner of the configuration is frozen? So this probability should be zero, or sorry, it should be 1 if you're in the frozen region. It should be 0 if you're venturing out of the frozen region. And this was studied by Filippo Colombo and Andre Pronko in a series of papers, 2007 to 2010 and beyond, probably. They did lots of work on this. It turns out they have several different formulas for this emptiness formation probability. And they depend on knowing where that top, that type 5 vertex is in the first row. So that's kind of the first ingredient in their formula is to understand where that, where the arrow switch happens in the first row. And so if we call that random variable, the location of that type 5 vertex lambda n, there's actually a formula for the probability mass function of lambda n, which is in a older paper, also Pronko and a couple of other co-authors. But then this is their formula for the emptiness formation probability is pretty complicated. So I just want to put it up here just so we can see that it's complicated. So I write down a generating function for a probability generating function for the lambda n. And then here's a complicated function of S variables, which is it's a determinant of that generating function with some other factors divided by a Vandermonde. So it's some kind of multivariable generalization. And then here's their formula, or one of their formulas for the emptiness formation probability. It's a big multiple integral. One of the ingredients is that S variable generalization of the generating function for lambda n, and there's some other factors. It's kind of hard to work with. But nonetheless, Colombo and Pronko did work with this formula and some other similar formulas. And again, not rigorously, they made some assumptions on how this integral should behave when n is big. They were able to do some asymptotics, and they found some way to characterize the Arctic curve throughout the phase diagram. In general, they found that the Arctic curve is non-algebraic, but at certain points it's algebraic. So here's the formula they found at the ice point. It's relatively simple. It's algebraic, but it's not smooth at the at the touching points. Yes.
So you mean by non-trivial, you mean like transcendental, or like it satisfies some other equation?
Wait, say that one more time.
When you say non-algebraic, do you mean like there's just no formula for it at all, or just like,
I mean, it's really not algebraic. Yeah, it's
like there's just no formula.
I guess in general, maybe there's some implicit formula for it, but not necessarily explicit.
Probably a solution to PDE.
Not that I know of, but I don't know. There's a lot I don't know. So
just to wrap a little bit to show the formula again. So is there any similar result for this function we see? And it's transition probability to ASAP or
I mean, it looks like one of those formulas, right? I don't. They look the same. Yeah, but I don't know. I mean, I looked at this a lot, like when I first saw it in 2009 or something, and I thought that was around the same time that Tracy Whittam ASAP paper came out. So I thought I could try to understand this one using their approach to ASAP, but
so I think now there is an understanding of it using beta onsets, and you essentially what ends up happening, you run an ASAP from the bottom and ASAP from the top, and they have to match in the middle, and it's the probability that both copies of ASAP match in the middle. So it's the product of two.
It's the same.
Yeah,
same as this emptiness. Oh.
Yeah, it's related to this emptiness.
Okay.
But in that case, it's the XXC model, which is a continuous version of the six-vertex model. So there is some relation, but it has twice as many contour intervals as ASAP because it's two copies working together.
Okay. Cool. Okay. There's another method to try to understand the Arctic curve, also in physics, which was developed again by Clomo and a different collaborator, Sportiello, which is the tangent method. And I'm not going to describe the tangent method, except to say that it also relies on knowing where the Arctic curve touches the boundary. So that's like a key ingredient in both methods. And they use this tangent method, again, non-rigorously to get the same results on the Arctic curve. And amazingly, Amal Agrawal was able to justify this tangent method rigorously just at that ice point A equals B equals C. So there, actually, this is a theorem now, thanks to Amal. But outside of the ice point, or the alternating sign matrix point, and the free fermion line, it's still an open question to find a rigorous proof of the shape of the Arctic curve.
What about fluctuations in this ice point?
There's one paper, very recent, just from last year, was Arvind Iyer and Sunil Chida and Kurt Johansson. It's like, yeah, they don't approach the fluctuations directly. They like draw a line and find fluctuations find the probability that the fluctuations don't hit the line. So it's kind of like the fluctuation should be the Airy process, and they find that something like the maximum of the Airy process.
Okay, so, and this would be for delta not equal to 0 for something.
That would be just for the ice point, just for the the alternating sign matrix point.
That gives you a non-zero delta.
That's a non-zero delta, yeah. Yeah, that's true. But that's the only, just at that one point. And other than that, actually, I don't know any results even in physics on fluctuations.
Okay. But that's for a specific marginal of the fluctuations.
Yeah, it's like yeah, it's functional of the fluctuations.
Okay.
Yeah. Okay, I have 1 minute left. I should tell you what my small contribution is. So this is what I tried to understand. This lambda n, the location of that lone type 5 vertex in the first row, it's a key ingredient in both of these methods. So I just wanted to try to understand it rigorously. And actually there's a formula for the generating function for the lambda n, which is not too difficult to get out of the work of Colombo and Franco. Here it is. It's a determinant very similar to the determinant which gives the partition function, which we can understand in terms of orthogonal polynomials. The only difference is the last row is different. But we can still understand this in terms of orthogonal polynomials. So here's a formula for the generating function for that lambda n in terms of orthogonal polynomials. It's something really explicit times Laplace transform of these same polynomials that appear in the analysis of the partition function. So this is a formula I wrote down like 15 years ago in my notes, and I never did anything with it for some reason. But then I heard Filippo Colombo give a talk last year about this. He said, "Can somebody understand this?" And I said, "I think I can." So, so I could. So here's the theorem. The generating function for this lambda n, you have to do analysis of that Laplace transform, and you have to understand what the orthogonal polynomials are. But if you do, you can find an asymptotic formula for that generating function. There's a change of variables, which, did I write it down somewhere? Ah, yeah. So I have to write z is equal to some change of variables in terms of signs. And it maps the complex plane into a strip in the new variable. And so this is an asymptotic formula, which gives it gives the leading term in the asymptotics and then also the constant term. That leading term actually had been computed before by Colombo and Franco. Again, non-rigorously and just for positive z's. So this extends it to the complex plane and also gives the constant term in the expansion. And what can you do with that? Well, if you know the leading term in the asymptotics of the generating function, you can write down things like a large deviation principle for the random variable, which I don't probably have any time to explain, but that's okay. And you can write down a law of large numbers, so you can figure out asymptotically where the Arctic curve touches the boundary. And that had been done already by Colombo and Franco. So there's a formula here for the point at which the Arctic curve touches the boundary. So they wrote that in their papers 15 years ago or something, 14 years ago. So what's really new is that if you want to understand fluctuations, you need to know the constant term in the asymptotics. And so I can prove then that the fluctuations of that touching point are Gaussian. Actually, it's a central limit theorem for the touching point. Okay, and this is the formula for the for the variance or the standard deviation, I guess. But that's it.
And what parameters on this?
What's that? So this is, yeah, I didn't say, sorry. This is everywhere in the disordered phase.
Okay.
Yeah. Yeah, outside the disordered phase, the same thing should work, but the analysis is different. So you have to work harder.
You don't find any KPC or 1/3 scaling?
No, so at the boundary, the scaling is n to the 1/2, and it's Gaussian fluctuations. And then as you move away from the boundary, the scaling changes to KPZ scaling. But yeah, so this is kind of a first step. As I mentioned, I'd like to extend that result to the anti-ferroelectric phase as well. So that result was just for this disordered phase. It would be nice this was a result about just the top row, but it would be nice to extend it to a result about the top 5 rows and show that, that the ones in the top 5 rows are governed by the GUE minors process, as Vadim did in the alternating sign matrices case. And what would be really great would be to try to take these formulas for the generating function and plug them into the emptiness formation probability formulas and see if I can get a result on the Arctic curve throughout, for all values of parameters. And then, fluctuations is maybe possible. I don't really know, but that would be also very nice to have a result on outside of the free Fermion case. Okay, only 6 minutes over. Thanks for not stopping me. Thank you all.
Thanks for that great introduction. Now I'll open the floor to questions. I think there's an obvious question for all of us right now. What's this picture of?
Oh, that's the most famous place in Oregon.
Oh, I should have known this.
No, I don't know if it's the most.
Where is it?
Oh, there was a movie from 1985 called The Goonies. It took place in Oregon, and that was the main thing I knew about Oregon for most of my life. And this is a picture of the some big rock in the
there was a
in the
treasure
ocean.
in there.
There was a treasure in there. Yeah.
Okay.
Yeah.
It might still be there.
Yeah. All right.
But any questions in here? If you're online, feel free to unmute yourself to ask a question directly or type it in the chat. Yeah, so
there's a chat.
There's a chat question. Cannon Beach.
Cannon Beach. Thank you.
Ed Weyermeyer.
There you go.
Give me the answer. Yeah, so I'm interested about this emptiness fluctuations for delta equal to 0. And I guess you did the first top row, and then you can also like scale n as the size is growing, right? The nth row.
Nth row.
Yeah, because you did the top row.
Yeah, I mean, there's some symmetry that if you know the top row, you know the bottom row, you know the left and the right.
N over 2.
Oh, N over 2, the middle.
Or like your scale, like somewhere in the bulk instead of like being near the top or near the bottom.
Yeah, I mean, if you're in the bulk, then it's a different scaling. As you said, it's again to the 1/3 scale.
Yeah. Okay. Yeah, that's where I was confused.
Yeah.
That was that. Any other questions? All right. Well, great. Let's thank Carl one more time.